This is lecture 10, and in this lecture, we will discuss the lateral equations. And in the first mini lecture, we will study the Rudder effect. Okay, so for the Rudder effect, what happens is, and assume now we have positive rotor deflection, and we can see the rotor has a positive deflection of delta R. And what will happen? So, because of the deflection of the rotor, the tail plane, the vertical tail, will have larger camber, and then there will be a positive side force YR produced on the fin. Okay, so imagine you have a side force, positive side force, YR. What happens is the aircraft, now we move to the right-hand side picture, and the aircraft will on the negative yaw, so we have a yawing angle, negative phi, and so in this condition, the aircraft is on the positive side slip, right? On the right-hand side, it's on the positive side slip. And in this case, now we are focusing, moving towards the fin on the side slip, and you can see now the wind is coming directly from the top, so the fin on the side slip is under a positive angle attack, and then there will be a side force towards the left, so it's negative, right, in magnitude, negative in sign, so it's negative YF. So there will be a negative force, side force produced on the fin again, and assume the aircraft is on the equilibrium in a force balance, and then we have YR should equal YF. So now we find the equation. This is what we want. YR equals YF. Okay, from the previous scenario discussion, we know there's side force produced on the vertical tail, and we know YF equals YR. And especially YR can be expressed as minus AR delta R times half rho V squared times SF. So AR is a lift curve slope for the fin rudder combination, and the VF is a true air speed at the fin, and normally similar as the aircraft true air speed. Okay, so we can find the side force YF, the expression for YF, and the target later of the derivation later is to calculate how much deflection of delta R is needed in this maneuver. That's a rotor deflection angle. Okay, so we know the side force, and then we can calculate the yawing moment, NF, so which is due to the side force YF. And then we have YF times LF. We are quite familiar with this, and LF is a moment arm, which is aerodynamic center between the fin and the CG, aircraft CG. So we just times LF. Okay, and then we find the dimensionless coefficient Cn. And remember how to find the denominator to non-dimensionalize the moment, which is half rho V squared times SB. And eventually we can have minus AR delta R times SF LF divided by SB. And we are now familiar, SF times LF divided by SB can be simplified as the VF bar, which is called the fin volume. And we are quite familiar with this coefficient. So the yawing moment due to Rudder angle and can be Cm delta R. So that's the aerodynamic derivative. So it becomes minus AR times fin volume. From the very first slide, we also know the aircraft is under a side slip. So the yawing moment due to side slip can be written as Cn equals Cn beta times beta. So that's Cn beta is the yawing moment due to side slip angle. Okay, similarly, we can write down Cn beta equals AF times fin volume, and so it's kind of comparison with the derivation, the conclusion from the previous slide, Cn delta R. That's the yawing moment change due to rotor deflection. Okay, and so here's something we need to pay attention to, and there's also a concept called propeller wash or proper wash. So in the case of propeller aircraft, so for example, in the picture showing on the top right corner, you can see the light aircraft is driven by a propeller, and the AF, that's a slope, lift curve slope of the fin rotor combination. The AF is affected by the so-called propeller wash because a propeller will produce some helical structures which affect the actual angle of attack of the fin. So on the side slip, the propeller wash axis is no longer along the x-axis. This will produce a change, so which is partial sigma, partial beta times beta to the propeller wash angle sigma. And so in the expression, we can say Cn beta, and there's a bracket which reduces the effect of the fin volume. So that's what happens. So the propeller wash on the if the aircraft on the side slip condition, the propeller wash will reduce the Cn beta. So that's what it says. Okay, so just remember this kind of concept. And then, so we've derived Cn beta and Cn delta R. So that two aerodynamic derivative will contribute together to Cn. That's the yawing moment, because in one part, the rotor deflection will produce a moment, and also the side slip will also produce a yawing moment. So they collectively contribute to the aircraft. So we just put them together, sum them up, and then we do some a bit analysis, and we take out the common term, which is fin volume, and then in the bracket we have some parameters, and so that's what we have. And if the steady slip applies for the aircraft, for example, the aircraft is on a steady side slip, and if it's steady, there's no net yawing moment, which means Cn equals 0. So that makes simplify the problem, because the rotor opposes the fin, and then we just simply letting Cn being 0, so we can have delta R. So the delta R equals minus beta times Cn beta divided by Cn delta R. So if you have an aircraft and Cn beta, Cn delta are actually knowing, and if we know the side slip angle, and we expect the aircraft to be staying a steady side slip, then we can know the delta R, which is a rotor deflection angle. So that's what we are going to talk about. On the steady side slip, how to calculate the rotor deflection. So that's for this lecture.